Well, welcome. Thanks for having me. Thanks for having me, Professor Giegel. And Jem, one of our interns who's TAing our class, the Hyperloop design class here, has been one of our prize pupils that lured away for one more semester here at Purdue, and then we're getting them back in a few short weeks. So there's a whole backstory that Hyperloop is about, and it starts before the Elon white paper, and that's one of our founders, Shervin Pishvar and Elon, were talking about this concept together, and Shervin sort of put Elon on the spot in a web summit, not all that, a couple years ago.
Yeah, you have that we've discussed before, which is Hyperloop. And right. I would love for you to tell this audience what that is and how it could change our world. Again, thank you.
It's this cross between a Concorde, a railgun, and an air hockey table.
That's it. So I think the Hyperloop team here knows it's just that simple. And with that, I want to maybe take a little bit of a poll before I get into it. So how many engineers do we have here? All right. Do we have any business folks? Oh, I saw one in the back. And then what's our breakup? Do we have civils? How many civils? Okay. Electrical? All right. You guys always sit together. I live on mechanical and aerospace. Okay? All right, and I think this, to the point made earlier, this is really kind of an all-encompassing project and a really good use of all the skills that you've learned so far. But that's the Hyperloop Classic, and that's the white paper that Elon outlined in the fall of 2013, and I'm sure most of the people in this room are familiar with that. And that was the starting point. And at Hyperloop Tech, we've really kind of taken it to the next level and moved it to our version of that. And our version of that is this new mode of transportation. So we're looking at transport inside of a fully enclosed tube that has electric propulsion and brakes to start and slow the pod down. And we'll go into all these in a little bit of detail, and you get to see the hardware that we're making. And then inside the tube, we've got an ultra-low pressure environment, so roughly 1/1000th of an atmosphere, or like flying at 160,000 feet of elevation. So 4 times higher than the plane I flew on 12 hours ago to come here, and Jem has me running around like a crazy dog. But that's a big part of the system, and that's why we've got the tube. We've got the compressor on the front to reduce the effective drag of the vehicle. And then we've got the levitation system, which is the question I've heard the most today from the different groups is, what are you doing? How are you doing it? And we'll talk about what that looks like. But from a high level, we're looking to move anything and focusing on people and cargo as the foremost thing. And if you think about what Hyperloop is long term, it's a new way to get from A to B. And for people, that means really fast transport. It means safer transport than exists currently today. And for cargo, that means the on-demand economy that we live in and work with today is going to be facilitated. So you've got one distinct, Amazon hub that might be in the middle of North Dakota feeding the entire United States with same-day type of delivery. And the last mile with automated vehicles and drones and all of that is really going to be a seamless way to integrate the future together. And we're looking to move it anywhere. So there was a couple civils in here, so we'll start with the land routes. So one of the things about high-speed rail is it's meant to connect 2 cities together, except along the way it divides the entire corridor. So it's meant to connect people, but it divides them at the same time. And Hyperloop offers a solution to not do that anymore. So instead of having this no crossing zone or no whatever zone, we can have an above ground distinct pylon structure, which is part of our low-cost type of system, and that allows easy access underneath. You can have no grading needed, none of this stuff that high-speed rail would need, and none of the stuff that highway would need, and you can do it at a much smaller footprint in a more sustainable way. And then ultimately, we're going to move this into the water. So if you think about what a water route means, that means if we went from Los Angeles to San Francisco, we would do that in the water. So you get rid of a lot of these land right issues and a lot of the potential hiccups and hurdles of getting a major infrastructure project installed. And one of the other things that's really interesting about the water routes is what it can do to ports. So if we had offshore ports So let's take the Port of Long Beach, for example. We're constrained in this really high-value area. You know, it's beach city, Los Angeles, California is one of them. And it's congested, it's constrained, you can't expand it easily. So if we take a Hyperloop and we push it out to sea, say 10 to 20 to 30 kilometers out to sea, the developers of those ports then say, all right, I can redevelop this land, I can make my port inland at this much cheaper land, then I can expand my port in a very organic way, and I can move it in further inland and then facilitate a broader network of Hyperloop hubs. So all those things really go to what the benefits of Hyperloop are, and I think a lot of the teams here have identified, I think SpaceX has done a good job of forcing it on the greater community is how do you make your system viable? So these are just a couple of the things that make our particular system viable, and it's weatherproof. So in areas that are cold, snowy, rainy, stormy, you know, imagine a transportation system that's unaffected by the weather. I mean, that's a massive, massive, massive improvement. It's unrestricted with the right-of-way, as we talked about. It's cost-effective. We're looking at costs on the order of about 60% of high-speed rail for technology costs. And that's 60% cost for a machine that performs 2 or 3 times at the speed, which is a massive, massive upgrade. I mean, that's essentially getting, you know, a Ferrari for the price of a Fiat. And as we move forward, on-demand departure, so we're looking at, you know, cranking through these pods at a very high throughput so that we can get as much cargo and volume through here as possible. And then inside we've got the autonomous revolution, of course, the driverless, ultra-safe vehicle. I had the privilege a couple weeks ago of being at the KTH school in Sweden, and they're really doing some cool work with autonomous integrated trucks together. And so looking at doing that for the Hyperloop. How do you do that? What are the challenges associated with these speeds? And so that's a really, really interesting design problem from a control side. High speed capable. It can tie into the grid in a carbon-free, energy-elegant way, and we're not looking to do, you know, this old-school, dirty technology. This is a much cleaner technology. There's not grease everywhere. There's not, you know, this is really what the future looks like, a clean, elegant solution. And then ultimately, various forms of braking. So we'll kind of skim through this real fast. Any of you who've traveled at any point in your life already know all of these different things. And it's an expensive mess. You know all of how congested everything is. You know how long it takes to get everywhere. And it's not that way just here in the United States. It's that way kind of across the planet. And it's dirty, it's dangerous, it's unsafe. So looking at all of these different things to make it better. And we truly believe that Hyperloop can do it. But it can do it in a way that meets the demands of the future. So all of the major forms of transportation are going to double in the next 15 to 20 years. So we're talking about a massive market opportunity. So for the couple of business development people that were in here, you know, they're going to spend upwards of $150 trillion on infrastructure projects in the next 30 years across the world. So a very small market share for a brand new technology makes a very big company. And this isn't, you know, apple pie technology. This is disruptive technology. These are the 4 modes of transportation, and the one thing I want you to think about in here is how many people have great-grandparents? Oh, good, all of you. So your great-grandparents could take the same 4 modes of transportation that we can. They can take a boat, they can take a train, they can take a plane, they can take a car. I mean, we're all engineers. That's somewhat embarrassing, especially like most of us are mechanical or aerospace engineers. You know, we're still making the same things, and they're not getting appreciably better. And of course, Hyperloop's going to be the solution to all of those things. So if we're going to look at the team, I mentioned before we had one Purdue alumni who's going to start with us full time, Jem, and he's doing a lot of our aerodynamic work. So the detailed CFD and drag and lift studies of the compressor as well as the pod is a unique challenge. And Jem has spent a lot of time in his past during his PhD really doing that work. And then we worked out a great situation where he gets to come to sunny California in winter. Just remember that when he leaves you in a couple of weeks. That he's going to come out, he's going to finish his PhD, but he's going to be doing it on stuff that's related to Hyperloop. And we had, I believe, 6 or 7 interns last summer. A couple of them went back to school, and we've hired 3 of those on full time. And we're continuing to look for that. And if you're looking for anything, and we'll get into all the different types of roles that they can have, but the teams here, the experience that you're going to gain in the pod competition is going to be invaluable. And that's why we love the pod competition, is we can find the best and the brightest. So our board of directors looks like this. You saw Shervin at the very beginning. He's one of our founders and is the managing partner at Sherpa Ventures. So they were part of our Series A round of investment. David Sachs is a former CEO of some companies you may have heard of, PayPal, Yammer, Zenefits. Jim Messina is one of our political influencers. So this is a really, really hard engineering challenge, but it's probably equal to or more difficult from a regulatory standpoint or from a political standpoint. So Jim has quite the connections and has led quite a few different things and has already got quite a few great meetings and connections for us. Peter Diamandis, the name's probably familiar to the technical community, just a great visionary. Joe's company, Formation 8, led our Series A round of investment and has been just a stellar partner for us. Emily joined us as another operating officer, as a board advisor. And then this is probably one of the biggest catches, and I'll go in shortly into kind of the timeline of the company. But Rob Lloyd joined us in September as the CEO, and he used to run Cisco. So he was in charge, he was president of Cisco. He was in charge of 45,000 people. He left Cisco and came to a 45-person company because he really believes in this vision, and I've had the privilege of getting to see the man in action, and it's really a testament to the team that we've built, to the product we built, and to the really transformative, disruptive nature of what Hyperloop is. So we'll hear him in a little bit. The team that we built, this is a little bit older slide, and a little bit about my background, and I'll just kind of skim briefly, but after grad school, I was all set to do a PhD, all ready to do some boundary layer transition and hypersonic flow, and I interviewed at SpaceX, and I came back and talked to my advisor, and we talked about the PhD, and I said, there's nothing I'd rather do less on this planet than what you just described. So it was also a little SpaceX influence, and so that sort of lured me away, and it was great. I mean, going to a company where at that time we hadn't had a successful launch, and going to a company where they gave you a massive amount of responsibility for no reason other than you walked in the door and you were the next man up. So I got the privilege of doing all the thermal, fluid, and structural on the Merlin family of engines that are flying on the rocket right now, the Merlin 1D first stage engine and the vacuum engine. The little Super Draco engine up here on the spacecraft, a couple little other test beds you can see down there, and then this microgravity fluid stuff, which I knew nothing about. They just said, go figure it out. And the only thing I knew about surface tension and microgravity was one paragraph in my fluid textbook. And I'd taken 7 fluid classes at that point. So that's sort of the environment we're trying to build. There are specialists around there. They take these young engineers with formable minds, and they teach them how to be engineers. And that's what we're creating and we're trying to foster there. So I came from a background of all engineers, mom, dad, sister, wife, just a really disturbing group of people. So much so that actually when Dragon docked with the space station for the very first time, it was the first night of our honeymoon. So those of you who are married, I'm sure you have your own visions of what your first night on your honeymoon were like, but mine was with the laptop up, my wife and I sitting on the bed watching spacecraft dock with the space station. So that's one for the keeper, long time from now. Wanted to go to a small startup, wanted to get a little bit more experience, and something I'd highly recommend. And a lot of the teamwork that you're doing, I mean, Paul's talking to me about building this kind of Hyperloop team, and it's challenging. It's challenging doing a small company. So EchoGen Power Systems was a small company, about 40 people when I joined in Ohio, and we were doing something that nobody had ever done before, which was a industrial scale, supercritical CO2 power system. And we did it. We built the first one in the world. You can see it right there in that little blue sky picture, the only day it was ever blue in Ohio. And And it was great. It was a great learning experience. You learn how to talk to people, communicate your ideas. It's something I'd really like to stress is you're no good to anybody around you if you can't communicate the ideas you have and the quality of them and make them understand, whether it be some woman who doesn't speak any English on a plane or your professor who you can have a 3-hour conversation with. It's just as important for either. And then after that wasn't going quite the way I wanted, I popped back out to California to do some work on Virgin Galactic, the Launcher One program, and about a month after I started there, I got a text from Brogan, who I worked with at SpaceX, and he said, must meet ASAP. And he told me, have you heard of the Hyperloop? And I was like, oh, this thing. And so he's like, I've met Shervin, you should come meet Shervin. And it did this little thing where, at first I was a little skeptical. I went home and I started looking up transportation because I'd never really done it in my career. And then I started seeing like, man, this could be something. This could be something really big. And I want to be part of the team that does it. I want to put together the team that does it. And I want to find anybody out there who's going to have the idea that makes it work. So it's been a great kind of formative experience for that. And that's meant we've done a couple things. When we hire people, we look for a very similar trait. And I saw it today in the Hyperloop design class. I saw a lot of pictures of real hardware. So all of you out there, one of the things, especially when we're looking at young fresh outs or greenies, is take pictures of all the stuff you're doing. If you're on a lathe, take a picture of it. If you've built something, take a picture of it, because when you come in for the interview and you're going through your portfolio and you're going after, picture of this, you machining that, you ran some CFD here, it's incredibly powerful, and it helps you remember all the stuff that you did. And what we're looking for in more experienced people are people who've built stuff. So we built rocket engines, spaceships, electric vehicles. This is a fusion reactor. It's a satellite. That thing in the center is a flying laser. It shoots a 1-foot diameter beam, chemical laser, and then it farts out this noxious gas to the side. And we've got the guys who designed a control system. So when the plane's twisting and wiggling and falling, that beam is staying exactly on its target. So these are the type of people we're looking for, people who've built stuff, people who've built hard things, solved hard problems, but more importantly, people who don't have to be the experts, but want to be the experts. They want to say, like, how do I do this? And I saw that today in the class. I saw, like, why are we doing it this way? Why are we, that's what you got to have, that curiosity, because no one's ever built a Hyperloop before. And we have to learn how. So we'll kind of roll through this. June of last year, this is when Brogan, myself, in the middle, met Shervin, Jim, and Scott Stanford. So that was sort of our kind of kickoff meeting. The company, I got impatient at Virgin, and I just quit my job. And in November, reported to Brogan's garage. So I'd highly recommend doing that, because you can't put one foot in the kiddie pool if you want to jump in eventually. Just go for it. So last December, we were in the garage. That's not beer, I promise you. No. But starting point, we ended up getting our Series A round of funding December 22nd of last year. So this time last year, there were 2 people at Hyperloop Tech. 2 full-time people, and that was our starting point. So since then, we had a sort of coming out party, which was in February, we had a Forbes article that really kind of announced that we were a company and organization. I could re-engage with my friends socially and tell them what I was doing. Because I had to quit a company that I worked with a bunch of colleagues and friends and didn't tell them where I was going, which, the speculation. That was the office. So this is very much the office that Jem came to, what was it, May? May. So this was in March, but that's what it looked like. So there's about 10 desks in there at that time. In the May time frame, we got our first section of tube. After May, we started this, and we'll talk about what this guy is. This is our own custom designed built wind tunnel, and we designed and built it in 9 weeks. Only one like it in the world. And you get to see how cool that is. We'll get to tell you why we did that. Shortly after that, we built our Levitation Rig, which, apologies, a little slow. You can see it here. That's testing our levitation technologies, and we'll give you a little bit more detail. Wind tunnel was operational at that point. By July, Rob had come to visit us. We had about 40 employees. This was the spot then. It was early motor development for the propulsion system. August, Levitation Rig was operational. September was a big month for us. We announced Rob as the CEO. We got a much larger office space, and we increased the team again. And at that point, Rob went on and kind of did his press release, and I think it's better to kind of hear from him. So, you want to play this video? Maybe click it. Maybe.
Million in second round funding, and the team now includes newly minted CEO Rob Lloyd.
I've seen what this guy can do in 6 weeks.
Exactly.
Lloyd spent 20 years in networking giant Cisco, where he helped drive the internet revolution.
It feels like we're exactly at the beginning of building out the next big global network, except it'll be a network for people and things rather than for data.
How long before the first functional Hyperloop system?
3 years from now, I believe that we'll be designing and constructing the first 2 or 3 production Hyperloop systems in the world. 5 years from now, we'll be moving goods and people.
There you have it, straight from the source. So he believes in the company quite tremendously, and it shows. I mean, the throughput we've got and the business development side since he's joined has been incredible. October moved up to 55 people. November 70. As of yesterday, we're at 74. So 2 to 74 in less than a year is quite the growth. It's painful at times, but at the same time, like, we're not doing something small. We're not making an app. We're making something big. Linear propulsion test, which is a big deal. We'll talk about that in a sec. And then a construction on our big test site will begin at the beginning of next year. So now into the nitty-gritty, the reason you guys are all engineers, the reason you're here, the engineering. So we've got the compressor, the low-pressure environment, levitation system, and the tube. So you know all this. I'm not going to go through it in detail anymore, but I'm going to talk about what we're doing and all the different things that we talked about in the past. So civils. We've got quite a few things here. We've got support and we've got tube. So support structure, pylons, tracks, dampers, earthquake mitigation, civil soil work, underwater work, all kinds of stuff there. And we're not going to do this the way other civil firms do it. We're going to do it in a much more cost-efficient way because we've got a very different system than what exists today. Tube side, biggest cost driver, if you look at the Hyperloop system, is the tube. Let's make it cheaper. Let's make it better. We've got some really, really cool stuff to do that, and we can take massive cost savings. We can take this, and we can make it one of the cheapest systems that's more robust than a steel tube could ever be. We're doing that optimization. We're doing that. These ideas are not the ideas that sit in your textbook. They're the ideas that you think about at night, and you come in and you execute, and you come out with a new way to do it. We'll talk about route at the end. Hyperpods, so the mechanical and the aerospace in here. We've got basically a chassis. How do we build this thing? What do we have to put in it? So propulsion, thermal systems, environmental control, you name it. How do we integrate that into a package? How do we reject heat? What's the thermal cycle on this? If I'm going to use a compressor, how do I cool it? Do I need to cool it? What does this look like? Is it existing technology or is it brand new? So all of this stuff is massive amounts of innovation and iteration because we can build a Hyperloop right now, but it's not going to be as cost effective as it can be long term. And so that's what we're looking to do is figure out a way to do this even better. And we've got some great ideas that we're working on in parallel with the big development. The levitation system, the question I've heard most often from every different school I've gone to is, what are you guys doing? Is it air bearings? Is it maglev? Is it magic? Is it fairies? And, we'll talk about it in a bit. How do we do it is, from a cost and efficiency standpoint, the propulsion side, nobody really makes these linear machines. Nobody makes them at the power levels we want. How do we do that? How do we validate it? Power side, looking to deliver 30 to 60 megawatts, pulsed power, and I'll tell you how much utilities love that. They're like, what? So how do we do that? How do we do it cost efficiently? Control side, these are autonomous vehicles. So all of that stuff, how do you make it work? How do you talk to the pods? If pod 2 has a problem, how do pods 3, 4, 5, 6 react to it? How do they deal with it? The route. This is something I'm ultra passionate about, is all of these little systems here are encompassed in the route. And they're encompassed by that in an optimization framework. So how do we create cost models, performance models, route models? Where do we tunnel? Where do we bridge? And we've got some of the most sophisticated optimization tools that are out there, and we've built on those with our own designs. And that right there is the key to the kingdom, because we can do all kinds of innovation here. If we mess that up, it doesn't work. So I talked with a couple of professors today who've done a lot of work with the grad students here with optimization, and learn it, use it, love it, breathe it. It's going to be the way of the future. So it's all building up to this, which is our development loop. So 2 miles, 3.3 meters diameter. So to give you perspective, you'll stand at one end and you won't be able to see the other end. That's real hardware. That's real steel. That's the hashtag steel is real catch line. But full speed, fully capable, showcase the main elements. We can hold pressure. We have a levitation system. We've got a compressor on the front, and we've got an electric motor in there. Complete system. And this will not be representative of the accelerations that people will see. This will be much higher, accelerating at like 2.5 Gs, slowing at about 4. But that's way harder than what we're doing for people. So it'll demonstrate that we've got the controllability. So here's a little bit more detail when we look at this. So DTLA, this is our development in downtown Los Angeles. So we're building this crazy tube. We've done it. You can see it right here. And we've welded it up. We've done vacuum testing. We've held vacuum in here for 10 days without constantly maintaining it. So our leak rates were way smaller than ever. In the initial group that we got to do these welds looked like I did the weld, or it was Jimmy's first coloring project. And the leak rates are well less than we ever thought they would be. So that's boding very well for kind of maintaining the system. And we're going to get more data as we get to the larger tube. So here's some more pictures of the tube. You get some rough dimensions of it. And then this is our vacuum test. How many people have pulled vacuum before? All right, how exciting is it? It's like watching paint dry. So we at least put a balloon in here so you could see that something was happening. And it didn't fail. I probably wouldn't have shown you the video if it did. Maybe I would have, depending on how great it was. But it held. This is just we can do that. We've got the ability. We learned quite a bit from that, and it's still part of our ongoing test bed. Compressor. So we talked about what this is, flying at 160,000 feet. The only thing that operates in this is either going up through it or down through it. Nothing flies here, nothing does anything, so we had to develop something to do it. And the computational tools, they're not the best. So we went out and we got a Purdue grad, to help us with it. And so we've got some CFD models. So these are some Navier-Stokes solutions that are conventional off-the-shelf codes. We've got some ideas for it. We've got some other more academic codes that we're using to verify it. But in the same vein we do everything else, we have to go test something because we're no good without the test. So we designed and built this wind tunnel. And you'll see that here. Let this play. But again, this is something that I called a vendor and said, hey, I'd like a wind tunnel in 2 to 3 months. And he said, we'll get you a design in 2 to 3 months. And I hung up the phone and said, well, that's not happening. And so we designed, analyzed, and built this with a team of 6 people in 9 to 10 weeks. Kind of give you a feel for the speed at which we execute. But this is a fully capable wind tunnel. We can adjust the test sections to measure lift and drag of our airfoil shapes for the compressor. We can put mini pods in there. It's really the only one like it in the whole world. And it can run continuously, which a lot of the other ones are just kind of just blow down type of wind tunnels. But it's a real great piece of engineering. It's a great showpiece, but it's providing a lot of very, very valuable data. And it's going to be an integral part to Jem finishing his PhD with Hyperloop at Purdue. So then our levitation rig, and the moment I know you guys have all been waiting for, and I'm probably going to disappoint you. But Initially, we were starting with air bearings. So this is some air bearing work. So we've got a little rig here, and you'll see it. And this might be why we don't want to use air bearings, at least right now. When do you think it's going to stop? Is it? Is it going to stop? Okay, it did. So that's our levitation rig. So we've got measurement sensors on that. We can measure lift, drag, we can measure stiffness characteristics, quite a few different designs. And we've moved away from the air bearings to a passive maglev system. And that offers quite a few things in terms of energy savings, heat transfer savings, cost savings, ride height. It's really quite a big change. And in my experience, I've never seen really a trade study that was so clear cut. So a lot of work to be done. It's a very different problem than what the SpaceX competition's offering, because they have a track ready to go and we're designing our own custom one. So had a big announcement yesterday, and I'll skip to the goodies. But this is our propulsion session. So cut that rotational machine in half, unroll it on the ground, and then you've got a linear electric machine. So this is a linear synchronous motor. And we get those poles just lined up, slightly offset, and we drag that cart forward at full speed. So you guys came at a great time. I'm glad I could announce this today. You want to roll the video? So yesterday we announced this, which is our propulsion open air test, which is testing the exact same motor that we're putting in the tube. So we've got our command center, which we've fabricated on site, and we can ship out to the test site. Here's our power electronics VFD. Switches for switching the different active sections of track. And then here's the length of track. This is about 200 meters long. Test vehicle, and you'll get to see basically this thing take off. And this still doesn't give it or do it really the justice that it does. And for example, a Tesla goes 0 to 60 in something like 3 seconds. This goes 0 to 350 miles an hour in 2. So maybe with, we'll offer some rides or some intern rides. It's going to be pretty exciting. But the real crux of this is you saw the little testing machines that we're doing for the levitation and the compressor and everything, but this is the test machine for the motor. So this is the exact motor that we're going to put inside the tube, and we're going to make sure that it works here on this scale before we buy 2 kilometers worth of it. Here's our route optimization. Sorry, would you be able to roll this one too? So this is a unnamed route in the southwestern United States between 2 large cities. Any ideas? Okay. So this particular one is, we've got these stations. So one of the great things about Hyperloop, what makes it so cheap, is inside this tube, the drag is so low that we don't have to have active track the whole way. We've got these discrete little stations that give a little boost. So only about 5 to 10% of the whole length of the track is actually active. So in between these stations, we slow down from about 700 miles an hour to about 620 over about 50 miles. So that's a very slow slowdown, and it allows us to have a really cheap, efficient structure. So the maglev that you see in China, the maglev you see in Japan, has an active track the entire way. We don't, and that's one of the reasons we're so cost effective, is that only in these discrete sections are there actual propulsion stations. This is a particularly windy route, so the optimization we did here is subject to G-loading and banking and all of that, but that's all part of our optimization toolkit that we're refining. Where are we tunneling? Where are we bridging? Where are we doing all these different things? And that's one of the things that we are going to be the best in the world at, because we've got some amazing people and some amazing tools already being developed. But that's in general like the route, and this is just part of it. The rest of it is how do you down select the design, the different performance aspects that you got. So the levitation system comes up with air bearing design, a maglev design, the magic design, the ferry design, and you can lay them all out, put them in the cost model. We can do quite a bit of optimization, figure out what is really the most effective way to do this, and that's where we're going to be the best in the world at. skip over. Oh. Next one. So this was, again, the office in March. This is what it looks like now. So we've gone from 6,000 square feet to almost 2 acres with about 18,000 square feet under roof. You came, and in the meeting we were in for an hour, there was a new wall built. And we had to walk around that wall to come out of the meeting. So it's really an amazing amount of growth, both physically and in terms of the team and in terms of the technology in a very short time, because we say we're going to do something, we say we're going to build that tube by the end of this next year, and we're going to do it, because that's all our backgrounds have done and that's all we've ever done. So this is some of the structure in the back, so that was the buildings inside. This is some more manufacturing space that we're getting. So we're going to build the first 2-3 pods. So come out, come to LA, let me know, josh@hyperlooptech.com. Come in, check it out, and you'll get to see the magic in action. This other building, this beautiful building that actually looks like a wooden aircraft hangar, is going to be more office space. We're getting pretty filled up. This is sort of back in June, clearing out a bunch of the space in between. We've got all this area to continue fabricating inside. This is our current manufacturing space, and you can see some of the test rigs in the back. So massive growth with that. We just announced in North Las Vegas, about 25 minutes north of downtown Las Vegas, is where our test site will be for the POT. And we announced that deal Tuesday. I've got 8 people at the site right now, getting this ready for the development of the POT project. So be splitting soon. There'll be a big group growing in the Las Vegas area. So if Los Angeles isn't your thing, maybe Vegas is. Maybe not North Vegas, but Vegas. But before we close it up here, I want to leave you with a couple of things. Is that when I first heard this idea, I thought this was crazy. It was just crazy. And I'm sure there's a lot of you out there thinking, I've read all this ridiculous stuff online, and that's the first thing they tell you when you're onto something, is that you're crazy. Then they tell you you're stupid. And then they tell you it can't happen. And then they're the ones saying, I can't believe it happened. So this is what happened 150 years ago. So 150 years ago, there were no apps, there was no CFD, there were no computers. And they took that network of rail with the sweat of men's backs and very limited machines and built that in 30 years. There's no reason to think that we can't do that with the technology we have now and the experience and skill set of every engineer that we've got here. So this to me is, if they could do that 150 years ago, what are we doing? So I know this can be done. I know it can be done here. I know it can be done around the world. And that's really it. And this is we're at the dawn here of, this is like 1902, 1903. Before then, the only things that could fly were balloons and birds. After that, people could fly. And that was a massive transformational part of the 20th century. And this is the 21st century, and Hyperloop's part of it, and it's going to be part of the 22nd and the 23rd. So with that, this is just a smattering of who we're looking for, what we're looking for. Please, if you're a design engineer, talk to me. Go on the website. We're hurting. We need more. And, have those kind of resumes ready to go, have the pictures. But across the board, a lot of development in the business area. There's a couple of business analysts, route data analytics groups. There's quite a bit of civil, electromechanical, electromagnetics, aerospace work, controls work across the board, and we're looking for great people. Check us out, hyperlooptech.com, hyperlooptech.com, @hyperlooptech on Twitter, and we're getting more out there in the public. We believe hardware is real. Hardware is what makes Hyperloop. You'll be able to come out and smell it, touch it, kiss it, hug it. I don't know, maybe if you've got big arms, but it's really happening, and you're looking at one of the people who's on the team of people doing it, and the more people we have, the better. But the next time, hopefully I get to come back here, you're going to see some really great stuff, and we'll send Jem back here, and he can do the talk. I'll make you take the red eye this time. But that's it. I'm probably happy to answer any questions if we want. I know there might be a lot, so.
If other nations want to purchase this technology from you, are there nations that you cannot sell it to, and do you have a price per mile that you can quote them?
So on the first question, there's nothing preventing us from selling this anywhere in the world yet. And we're certainly looking outside the United States pretty heavily for certain routes because there's a lot of people with money, private money in certain countries. In the United States, historically, it's been government money that invests in infrastructure projects. It's different in other parts of the world. So in terms of the exact cost per mile, we've got the cost I'm quoting for the 60% number is our greenfield comparison to greenfield. And when we look at a certain route, then we start really digging into where do we tunnel versus where do we bridge. And it's plus or minus that kind of 60% number, but we're looking around, I believe the number is 16 to 17 million a kilometer, and high-speed rail is around 25 for just the raw technology costs. We're not talking about the entitlement or the land costs with that. And that's kind of an apple-apples comparison in the same type of right-of-way, but it is a bit route-specific.
First, what is the meaning of the word levitation in this case? Still the word magnetic is organized very cabinet. In particular, what it means for the energy cost, if you're going to use any kind of electromagnetic wave with that. And the second part, what kind of accuracy need to achieve in the transfer direction of this axle? Millimeter, inch, whatever. What is the control system? What is the associated energy?
So on the, try to pick off some of the quick ones first. Order of 1 inch type of ride height. And energy cost of, so the system itself is completely passive. There's no active elements on the pod or the track. Based on permanent magnets on the vehicle and electrically conductive sheet on the track. Designed with a little bit of secret sauce on the track side. It has a bit of drag.
Magnetization costs energy, right?
It does, and it manifests itself in drag. So we've got the drag that you see on the vehicle now is predominantly electromagnetic drag as opposed to aero drag, about 50-50 to 70-30. And that is really a part of a lot of the optimization work that we're doing now. So we're making the trades of where do you put that in terms of, do you put power on the vehicle to do that? What are the costs and the weight penalties associated with that? Or do you have more frequent boost stations to deal with that type of setup?
That makes sense. One of the things we didn't quite talk about, but I'm just curious about is if you guys put any thought into the safety for the passengers. For the, if there's, for instance, a problem with one of the cars we're going to install in the middle of the tube, how can you actually get EMP or whatever in the actual tube if it's also in the vacuum? That could have some problem.
Yeah, so in general, there will be, if you're familiar with rail terminology, there's things called sidings, which are basically branches off of the rail track. And those will be every so often to offer essentially a off-ramp for a disabled pod. The pods themselves will have propulsion on board to take them. In the event of a disabled pod, they will have low-speed propulsion to take them to the nearest station, nearest kind of way station, at which point then the passengers in that can get out or some other thing can happen. In terms of like a tube breach or something like that, it's actually great because the levitation system is passive now. There's no active power required to do it. We just have drag. The breach in the tube would act as sort of an air brake. So it's a natural natural brake to slow down the pod. And so in that way it will slow to a stop. And in terms of if there's like a breach on a particular section of tube, there's what's not shown in any of these pictures is like these sluice gates, for lack of a better word, which are bulkheads between sections of tube so that you can isolate a problem. And all the vehicles are in communication with each other, so they know the pod upstream is having a problem. They can all slow down accordingly.
How do you plan on keeping the pod from rolling?
Yeah, so definitely banking in the turns, trying to take the majority of the G loads down through the center line of any person. And stabilization with the, trying to think about what I want to say here without giving too much away. The part where it's actively powered, the motor gives that guidance in that particular spot. And then when we're not guidance, the track design, think of yaw control on a plane or roll control on a plane. How do they mitigate those type of things? They've got, ailerons in different spots on the plane to do that. And we're doing that with a passive system, a active system that's actually giving the lateral stability side and adjusting our suspension system kind of control parameters. So there is a suspension system on there to deal with any bumps or hiccups that may be in the track.
What is the power source for the system going to be? Will you be purchasing power from the distributor, or would you be producing your own power somehow?
So right now it's going to be, for the dev site, straight off the grid. And that's really the path forward. Because if we go straight with like solar on the tube like the original white paper talked, that limits the throughput. If there's only a finite amount of energy it can catch. So we can certainly continue to put solar on the top, but it will be directly tied into the grid. And we'll have a energy buffering system so that we're not pulsing this power. So we've sort of got a continuous drain, and then we've got effectively something like a capacitor or the like to discharge these pulse power.
So like for the compressor, you obviously put a lot of power to it. When you talk about how to heat dissipation, that is that because you're in a low pressure environment, it's kind of more difficult than just air cooling.
So with the compressor, the design that we've looking at now is a self-contained design. We're not running it, we're not baselining air bearings, so we don't have to cool that. So effectively, we can compress the air and actually do nothing to it if we really wanted to, and just dump the hot compressed air out the back and let it equalize or reach an equilibrium with the tube structure. So that's the nice aspect of it, is you're just adding compression work to the raw gas itself, and then you don't have to heat exchange with it if you don't want. And in the extreme case, long term, you can recover some of that power through a couple of ways, or you can translate it into thrust, or you can do a whole host of different things.
You had mentioned Hyperloop going underwater. Do you know how deep it would go and how it would be supported?
Yeah, so definitely not at the bottom. Good. I think we've got a position on here. Hydraulic engineer, you got it. Definitely not at the bottom, not at the surface either, but around 60 to 80 meters, there's something really special that happens, which is absolutely nothing. It's below the deepest draw ships. It has, in areas near the shoreline, you can easily anchor to the bottom for that. We've got a couple of ideas, a couple of concepts, I should say, that we've taken some serious look at that aren't anchored to the seafloor. There are other things, I'm not going to talk about the details of them, but in principle, ones that are near shore are conventional type of pipeline technology that are just not designed to operate on the bottom of the sea.
You mentioned how the propulsion is basically a series of pulses along the track. So how does that detract from the pod's ability to brake?
So the braking and the propulsion system are, let me kind of clear it up. There's a main propulsion system, and there's sort of a main catch system. So at the very, like your destination terminal, you'll have something that looks exactly like the thing that accelerated, catch it, recapture that energy regeneratively, just like a Prius does or a hybrid does. In terms of stopping in the middle, there's the ability to onboard adjust the way we're doing the levitation system that can make it far more draggy, and that allows us to control the speed in a slowdown type of setting. And then you can also, with a bit more active control, you can, to an extent, speed it up, but we don't want to do that all that much because that puts a lot of extra machinery on the pod.
How are you going to deal with loading and unloading to maintain the banking pressure?
So right now we haven't focused a lot of time on the station design. There's a lot of deep technical work on the concept itself. So on the dev loop, we've got a holding cell, so to speak, at the one end of the the one end of the tube. Pod comes in, the main section of the tube, the long section of the tube is kind of continuously held at vacuum. And then this section comes in airlock style, opens up and moves through. And the real challenge with that is when we get to a specific route and we say, what throughput do we need on this route? How do you design the station? And this isn't going to look like an airplane terminal. This is not going to be like a big shopping mall. You're going to interact with this very similar to how you interact with a roller coaster. So we live in a world where there's still going to be TSA, but you're not hoping to get through TSA to catch the one and only flight that leaves at 10:20. You're going to get there and you say, okay, I'm going to San Francisco or I'm going to wherever. And this discrete movement, there's 20 other people that are getting there. And if you miss the 10:20, you get on the 10:25, you get on the 10:30. So there'll still be that security, but you're not like hoping to get through it. And it's just kind of a fact of life with the world we live in. And then the specific route will dictate what the station looks like, what kind of throughput do we need. But you hop on it like you do a roller coaster. It's not like boarding a plane. You can see the throughput that Disney World has. And that type of logistics is really integral to the station design.
Which do you consider the bigger commercial prospect, cargo or passengers?
I think passengers is far more sexy. Passengers is what gets people attention. Getting cargo faster is, less tangible than you getting somewhere faster. So ultimately, I think people will be what sells Hyperloop. But just like, Uber X is subsidized by Uber Black, I think cargo will subsidize people to an extent so that the people routes will be trying to keep a reasonable cost target for people to do that. And it's kind of a wishy-washy answer, but at the same time, it's very route specific. So if you looked at a Shanghai to a Moscow route, that's probably more cargo than it is people. So, but if you look at a SF to LA route, that's a lot more people than it is cargo. So I think long term, it's going to be much more visible from the people side, but we're going to get our chops wet on the cargo.
What kind of working class do you report on a daily basis?
So right now, we know what people pay for high-speed rail. And we've talked about us having about a 60% capital cost of that. And we know that our operating cost is lower because we're using less energy and we're not, grinding steel wheels on steel rail. We've got kind of a contactless system. So we know both of those things are cheaper. So we know we're going to be at least, 25%, if not more, cheaper for a given route type of cost compared to high-speed rail. So that's really the starting point. And then depending upon the market, there's different ways that you can incentivize certain routes or, loss leaders versus, money makers and whatnot. But yeah, it'll be just from the CapEx and the OpEx alone, it'll be cheaper than the existing modes.
So right now it's kind of a one-way loop. Like reading about return loops,
Always at least a two-way tube, at least. There's some routes that demand more than that, and most likely there'll be the ability to at least have three so that if there's maintenance or something that needs to happen, you're not going to shut down, SF to LA.
You said the pod will accelerate from 0 to 300 miles per hour in 2 seconds.
On
the passengers get that acceleration?
On DevLoop, not in real life. Not in real life.
Well, what kind of acceleration are we talking about?
Airplane acceleration. Yes. Yep, and that's from a passenger comfort side. This is so that we can showcase the core elements of the technology without buying, 10 kilometers of tube. Yeah, so the real ones will be 0.2 Gs or so, and then the D-cell one is the one that people feel less comfortable with because it feels like you're falling over. So that one will probably be a lower value, and there's quite a few good standards out there for FAA, and then the actually derivative acceleration called jerk, which is that feeling when you hop on the elevator and your knees get weak. It just gives you whiplash, all that other good stuff. So that actually limits your acceleration more than the other points, is keeping that like controlled environment.
Are both passenger and cargo going to use the same track?
They can. So the cargo container that you saw on the one slide is our baseline for the pod size. So that's a standard 40-foot by 8 by 8.5 foot cargo container. There's hundreds of thousands, not millions of them in the world. And that physical volume is the same size as the passenger compartment. And that seats typically 20 to 30 in first class style train seating with an aisle in the center and everything. So same tube. From the outside, it's going to look like the same pod.
Hey, so you got the factor of safety in the tube itself, because you're building a long tube and you want to minimize costs, but there has to be some safety, environmental impact on the tube and such.
Yes, so there's quite a few really great design standards out there for civil codes and everything like that that give factors of safety in terms of live loads, stability, collapse, or effectively buckling. And this will all be to those standards, and we're designing for 100-year life. Not the 50-year life of conventional sort of highways.
So does it require a new path, or can you use existing rail or road?
Using so yes, it can. Short answer, yes. The biggest limitation is how windy it is. And ultimately, like that one route I showed was actually following the existing rail line, which is somewhat speed limiting. And that's where we'll have to really do quite a bit of land acquisition, is when we do that optimization, if we have to follow a specific route, what does that do to time? What penalties are we paying for that? So in theory, yes, and we could actually go above the existing infrastructure. However, I think that's going to really limit our performance.
How would that deal with natural disasters such as like tornadoes in Oklahoma or hurricanes in South Florida?
Probably got a little bit more direct experience with the earthquake stuff that we've been looking. So the standard design practice for earthquakes in California is pretty rigorous. And using that information, and we know, there's different levels with different magnitude earthquakes. One is basically earthquake safe, I don't remember the exact numbers, but say 5.0 hits. You can't have the system shut down or have anything. It needs to be okay. 7.0 happens, then you've got the ability to like, hey, that's pretty infrequent, so you're going to have to come out and do some inspection, do some maintenance or fixes to that. And we know what based on our levitation system and the G-loading and the braking and all that other stuff, we know what deflections we can tolerate in the track. And so then we're reverse basically designing the rest of the system so that under those once every 200-year or once every 100-year earthquake levels based on the codes, that we end up with the system doesn't respond more than what's really tolerable. So it's probably an indirect way to answer that we're robust to all but the worst of the worst.
So like I San Francisco to LA, there's wildfires quite a bit of an issue in California. How would you address that issue?
I actually haven't thought about that one, so I don't have a really distinct answer for you. No, it's a good question, but on the outside of the tube, for sure, there's a passivation element from a corrosion standpoint. And right now that looks like concrete. So how well does that perform? And yeah, that's probably all I got for you. Good question, though.
So you've kind of switched from using air levitation, but you still have a compressor on the front of the vehicle. Have you considered using that compressor to just capture air instead of ejecting it out the back so that you can maintain the vacuum? Because you were already compressing it. It seems like you'd be kind of duplicating the hardware there, or would it increase the vehicle cost too much?
The compressor does a couple of different things. on the front. It essentially helps control your pod to tube ratio, your diameter ratio effectively, and then also controls to extent the amount of drag, aero drag that's over the pod. So it's a bit of a balancing act in terms of that performance optimization is what size compressor do you want on the front and how much compression do you want. And that's really very dependent upon the cost assumptions that we got is really the biggest driver as opposed to performance because we could make it, we could have no compressor, become very drag heavy, right? And then we just shift all that load onto the track and we have to have more boost stations. But those boost stations are expensive. So where does the trade happen? And that's, based on the routes we've looked at, it's different from route to route. So trying to kind of find a good optimum for most routes so we don't end up with, this pod can't go in this tube and this tube can't use that pod. And we'll do one more.
You mentioned that the tubes would be about 2 miles long. So I'm just wondering, in case of an air contamination, how long would it require you to vacuum out the air?
On the development loop one?
Yeah, for a 2 mile long tube, I imagine it would require a long time to vacuum out.
So right now we can pull with the pumps that we've sized and that we're planning on using, that can pull down within 4 hours, 2 miles. And it's really just a question of cost, is how often do you want to pull it down? Because if you want to pull it down faster, you just buy more pumps. All right. Well, thanks for having me. Thank you.